Hey everybody, and welcome back to Algebra 2 Online. So this last video in our conic sections unit will just be on solving systems of conic sections. And just to get started, I want you to think about the following question. So what is the maximum and minimum number of solutions that a system of two conic section equations could have? And let's assume different equations because, certainly you could just have the same like hyperbola or something as the system, and then they would have an infinite amount of solutions to that system. But you should pause the video, think about it. I've got pictures actually on the other slide here that's coming up. So hopefully you thought about it. The answer for the maximum minimum is, I think the minimum is definitely like not so hard to see, right? You could have something like upside down parabola and like a circle, something like that I'm trying to draw, that just touch in one spot. So you could definitely have one solution well, I'm assuming you're having a solution, I guess. So you could have one solution, but I guess if you also consider no solutions as a possible case here, you could even go lower. You could have, a circle, and then you could have like a parabola like that. So you can have no solution too. But if you actually assume a solution, then the minimum number of solutions is 1. For the maximum, it would be 4, which is kind of different maybe than you're used to thinking, but you could have something like a ellipse like that, and then you could have maybe a hyperbola like that, right? And so we're getting 1, 2, 3, 4 solutions. So you actually can't get more than 4. There's actually a theorem in math called, I'm pretty sure you pronounce his name like Bezau's theorem. But basically, this says that the maximum number of intersections is the product of the degrees. Okay, so basically, if you take a hyperbola and ellipse, let's take that example. Both of those have a degree of 2. They're parabolic objects in math, and so you just do 2 times 2, you get 4. So 4 is like the max number of intersections, and you can read about this if you want, but it's not really something that we necessarily use in this class. But there is actually a theorem for that in math, and it just says that the max number of intersections would be the product of the degrees of the two objects that you're looking at. All right, so these are like some other pictures. There's definitely other cases out there, but these basically sum up some of the main different things that you can get. So you can definitely get no solution. That would be no solution. This would be 1, right? This is 2 solutions, 3 solutions, and 4 solutions. So when we solve systems of these nonlinear equations, these conic sections, we're getting sometimes no solutions, sometimes 4 solutions, 3, 2, 1. All of those are very possible, and there's different ways to draw them. These are just a few examples of the ways we can get like 0, 1, 2, 3, or 4. Okay, and the way that we solve these is really nothing totally new. It's substitution or it's elimination stuff. So you don't even have to put these conic sections into like the standard form where we know the center and things like that. I mean, if you were trying to graph them to answer it, I guess you could do that, but a lot of times the intersection points might be really weird numbers that are just not easy to look at from a graph. So basically, when I solve systems of nonlinear equations, like conic sections, I just do substitution elimination stuff. So, if I take this first equation and I look at it combined with this, right, if you're going to do elimination, you need to try to get rid of all the x's or all the y's, right? And if I was going to do substitution, you just basically want to look for like some... so for substitution, you just want to find something like this y value is easy to solve for in terms of x, but you want to make sure that you're not solving for one variable and have the other, like have both variables on their side. So it's not enough here because you might have y squared and y terms. So we can't just like solve for this y because we'll have y squared terms there, right? So basically, still the same idea. It's just a little trickier sometimes when you do it. But, for these two, you definitely could solve for this y in terms of these three terms, which are just x terms or constant terms. And then you could take y and plug it in here and here, and you'd have all x's. Or, and this is probably what I would do, this set is pretty nice together because if you add these equations, you'll get rid of these x squareds, and you'll also get rid of these x terms, right? And so then we would reduce these equations to just y terms. So that's what I'm going to do first. I'm going to go ahead and add these two equations. All right, so, when we added these canceled again, and these canceled. We've got no y squareds here, so we just get 6y squared. Then we have minus 1 minus 47 is minus 48, and then these two add to 42. And so this is just now a quadratic in y that we can find the roots of. So I'm going to go ahead and do that. All right, so pretty nice quadratic. We can take out a 6 of everything, factors, we get 7 and 1. So now what we're gonna do is we have these y values, and we just need to use one of these two equations and plug in the y values and see what x values come out. So so this is kind of one that's looking like we're gonna be getting like at least 2 intersection points, right? Because we have 2 different y values here. We might get 4, but we're basically definitely getting some sort of intersection. So these 2 cases are definitely out, right? We're looking at like this kind of thing. So I would personally probably use the top equation because it's smaller, right? So I'm going to plug in 7 for the first one here. So we'll do minus 7 plus 127. And then I'm going to go ahead and simplify that. So if you plug in minus 7, you can simplify it down to this, and then it's just same kind of thing as kind of over here. You're just solving a quadratic. This one is pretty nice because it's another one that can factor. You have plus 10 and plus 6, right? And so we get minus 10 and minus 6. And so that gave me 2 intersection points. It's basically saying negative 10, 7. Let's do the answers in a different color. Negative 10, 7 is an intersection, and negative 6, 7 is another one, okay? And then basically what I just need to do is same kind of thing, plug into that first equation, the 1, right? So minus 1 plus 127. And then I'm going to pause the video here and go ahead and just solve this out. All right, so we get these 2 x values. And then we can just go ahead and pair those up for our last point. So where am I going to put this? I'll do it over here. So negative 7 and 1 is another point then, and negative 9 and 1 is another point. So I actually have a picture of this problem. So if you go and plug these 2 into like Desmos or something, you'll get these 2 graphs. So this first one is actually just a parabola, right? If you just move the y over, it's just a parabola. Standard form one has like a y-intercept of 127, a value of 2, and things like that. But basically, it's intersecting this hyperbola in these 4 spots that we just found. So when you do these kind of questions, you can easily, check your answers with a picture or something, and a lot of times the solutions won't be this nice, but just to start off, I wanted to do ones that are kind of nicer. All right. So if we're doing systems of equations, we would just do substitution or elimination like I just talked about. If we're doing systems of inequalities like this, basically we have to graph the conic sections and shade like kind of inside or outside the graph. So when it comes to doing systems of inequalities, you basically have to start by graphing, and then we'll kind of go from there. So, a lot of these, are a lot of what's in these two graphs are pretty nice, but we can do a little bit of simplification because we can simplify basically this a little bit. So, this first graph, I'll do some blue. It would simplify to this. And from there, we can go ahead and graph this thing. So its center is just at the origin, right? And the hyperbola, because it does have a negative, right, is a left-right one because the x is positive. So we've got to move 2 units to the left. Oops, that was 3 units. 2 units to the left and right. And then the b is the square root of 12, which square root of 12 is kind of a weird number. It's about, square root of 12 is like about 3.46. So we're just going to kind of have to do the best we can for the slope part. We're going to go from the center up 3.5-ish. So 1, 2, 3. 0.46 is roughly there, so about there. And then we're going to go up the same amount and to the left this time. And so these are my asymptotes, okay? And then we just want to try to make a graph that is in those asymptotes roughly. So kind of like that, okay? And this one is a solid graph because it's equal to there, right? Okay, so for the other one, we can see it's going to be an ellipse because these are different numbers and they're both positive. The center is 4, 0. This one is going to have to be dotted, okay? So I'm going to go ahead and just simplify that one a little bit. I think I'll just do this down here. Right. So this and this are the same thing, and then it tells me I need to go from the center 5 units left and right, and then 4 up and down. So my center again is 4, 0, so that's going to put me right about there. 1, 2, 3, 4, 5 over there. 1, 2, 3, 4, 5 over there. And then I got to go 4 up and down. So right there, and then right there. And then this one is a dotted ellipse, okay? And then, so for shading, we've got our graphs now, and now we just think about the shading part. So we want to shade everything. So if it's an ellipse like this that's less than here means inside the ellipse. And so we would basically just shade just all of this right here, okay? And then for shading the hyperbola, sometimes it's easiest to just plug in a point and kind of check for hyperbolas because the negative, I think, is kind of confusing at times. Here it's just literally less than, when they're positive like that, less than is inside and greater than is outside. Same thing with circles. And parabolas are very straightforward. We've done those for a while, but hyperbolas are kind of weird. So sometimes what I'll do is I'll just plug in a point. Like you can plug in you could do a vertex, like you do 2, 0, right? So if you plug in 2, 0, right? Or let's do like 5, 0, I guess. So just something like over here, because it's basically, is it shading here or is it shading here and here? And so if you plug in like 5, 0, that term would just go away, and then you would have 12 times 5 squared, right? Which is a pretty large number, right? 12 times 25. Definitely going to be greater than or equal to 48, right? And so that basically tells me that I do actually shade on this side of the hyperbola, so kind of on the guess, inside of it. And then the solution, though, right, is the overlapping shaded region, right? And so the solution is just this black area that I'm shading right here. So anything that is contained within the ellipse, but kind of to the right of this righter part, the rightmost part of my hyperbola. So, solving systems of inequalities with these is still the same old thing we've done. It's just a little harder because the graphs are a little more complicated, and shading can be a little bit more tricky, I think, especially for the ellipse. But basically, you can just test a number, and that's kind of the easiest way to do it. All right. So this is just one last little conic section question. So I want to write down the equations of two different ellipses that share a common focus point and intersect. After you write down the equation, I want to solve the resulting system to find the intersections. All right. So this is kind of a weird question. I'm going to start with a picture. So I think it's good to visualize like what's happening here. So what I think easiest way to do this is to take an ellipse like this that has some focus point here, and we're going to find an equation of like a basic ellipse that does that, and then we're going to have to share that same focus with another ellipse, like over here, let's say. And then there's definitely going to be like two like intersection points, right? And we basically just need to also find those, like solve a system of equations, okay? So for the purple one, basically what we're going to use is we have the c squared equals b squared minus a squared. So, this is our little formula for finding the distance. C is the distance from the center to a focus point, and that's for vertical ellipses like this. And then a squared minus b squared is the one that would be like for this horizontal ellipse here. All right. So what we basically just want to do is come up with like some a, b's that, like, if you subtract them, like the squared ABs, you would get some nice, just so you don't have to deal with like weird numbers. So I'm going to do, something like an ellipse centered at the origin like this. And then if you do 9 for A and 25 for B, 25 minus 9 would give you 16. And so 16 will be a nice C value. But, technically you can do anything you want. You just have to deal with worse numbers, right? So what I've basically made here is that this point right here is now, 0, 4, right? Because 25 minus 9 is 16, so this is length 4 is the distance from the center to the focus point. So I've got to get an ellipse that is basically shifted around enough so that it shares this focus point now, and it's like a different ellipse, okay? To do this, what you can basically do is just, you could shift the center to be like at the same height as this focus point, right? So it could be up 4 and y. And then we could be like over 4, right? So we have like x minus 4 squared, y minus 4 squared. That would give me like the center shifted correctly. And then I just need to make sure that, so here I'm going to use c squared is a squared minus b squared. So I need c squared to be 16, right? And so basically a has to be 25, or a squared, and then b squared has to be 9. And so I just kind of switch where the 9 and the 25 go. And then what that would give me is, because of how I've shifted it, this is actually 4 units away from the focus point. And then, so they share a focus now, okay? So these two equations do what I wanted. They share a common focus point, and they're definitely going to intersect somewhere. And then to solve the system, what I would go ahead and do is, this would be pretty gnarly to multiply out. So I would probably just solve for, like, x here, and then plug that in here, okay? And the intersection points are not necessarily nice, but we can definitely find them. So I'm going to multiply by, I'm basically just going to solve for x here. So x squared would be 1 minus y squared over 25. X squared over 9. So then x squared would equal 9 minus 9y squared over 25. And so x is just equal to plus and minus the square root of that thing. Right? And so that's what I basically need to plug into the other equation now. So you can see that this is looking pretty messy, definitely. This is a pretty gnarly little square root equation. And so if you go and you pop that in here, okay, it's even going to get way worse because you're going to have to square this out and square this. This isn't that bad to square out, but basically if you use a calculator to help you here, you can plug all this in and you can get this down to basically this, which, as you can see here, so if you substitute it in, this is just the positive one, you will get all that, and it's obviously a big mess, and so I would just use like a calculator to help you solve this. So I would use like the 0 button on check, obviously just the real roots of it, because the imaginary roots are not going to help me here. I'm not looking for the imaginary intersection points, but basically if you use the calculator, you're going to get y is like about 1.07 or 4.813. And so once you get those two, those are, so y of this is 1.017 or 1.07, and then this is 4.813, and I would just get that from a calculator. So I think you can even, all you have to do is square this out, get it into this form, then you can just use your calculator. And then getting the x value is not bad because you can just take these two numbers and plug them in, and that all is actually pretty nice. So the x values that go with those y values are, running out of room here. I'm going to erase this. Whoops, I'm going to erase this. So the one that goes with the 1.071 is 2.931, and then the one that goes with the 4.813 is negative 0.813. And those are just, those are pretty quick because they literally just come out of this. So this is the one part of this that's pretty messy. You basically just have to multiply this out, combine some like terms. I don't even think you really have to combine them any like terms because you could just go and just plug it into a calculator, I think even from here, and you would still be able to, it would be able to graph that. So you would just obviously have to graph, we subbed in x, but you could sub in, you would just have to type it into the calculator as the independent variable as x, because it won't understand the independent variable being y. But besides that, you just switch the two around, and the roots would just be the same numbers. So those two things, and you could check this on Desmos. You could go plug this and this into Desmos, and those two things would equal these intersection points.